Good morning, everybody.
Good morning, sir.
Good morning, sir.
I have joined.
Yes, sir. Thank you, sir.
Okay.
So shall I start, sir?
Yes, the external member also joined, so please start.
Good morning, everyone. On the external member, Sir Kansar, Sir Rubun Kumar Banya, and Nazarene ma'am, and my supervisor, Dr. Dibya Jyoti Bora. My name is Mainul Hoque, and today I will present my pre-submission thesis, work title HDL Implementation of Deep Learning to Cloud Edge Data Analytics for IoT. This research focuses on how deep learning can be effectively integrated into cloud edge data analytics framework to support IoT applications. I will walk through the motivation objectives, methodology, result, and future directions of my work. Yes. So here is the outline of my presentation. I'll begin with the introduction and motivation, followed by the objective of my thesis or pre-thesis submission. Then I will present the literature review, my proposed models and methodology. After that, I will share results and evaluation, discuss contributions and limitations, and finally highlight future work before concluding. The Internet of Things is expanding rapidly with millions of devices generating huge amount of data. Traditionally, cloud computing has been used to process this data, but it often suffers from high latency and bandwidth issues. Edge computing brings computations closer to device, reducing delay. So my research focuses on integrating deep learning into this cloud edge synergy to improve IoT data analytics. Problem statement. Despite progress, current task of loading and deep learning models fail to balance delay and energy efficiency. Reinforcement learning approaches often collapse under delay or sparse reward, leading to unstable convergence. Edge devices are resource constrained with limited CPU, memory, and energy budget restricted deep learning deployment. This leaves a critical gap. No existing cloud edge framework which ensures both stable convergence and efficiency simultaneously. Therefore, our research addresses this gap by introducing trace-aware reinforcement learning architecture designed to stabilize learning and optimize delay energy trade-off in heterogeneous IoT environment. So the objectives is structured around 4 main goals. First, I identify the issues in deploying a deep neural network directly on IoT devices where real-time execution is often limited by hardware constraint. Second, I analyze edge server-based architecture that allowed computations offloading to reduce latency and energy consumption. Third, I designed optimized cloud edge data analytics model that integrate deep learning for IoT application. Finally, I evaluated the performance of this proposed model against existing cloud edge baseline to demonstrate improvement in efficiency and stability. Literature review. The literature review shows that mobile edge computing evolved as a response to cloud computing limitations. But then cloud systems struggle with latency, bandwidth, congestions, and energy efficiency. So mobile edge computing shift computations closer to the data source, enabling real-time analytics for IoT applications such as autonomous vehicle and healthcare. However, Existing approaches still lack robust latency-aware learning models that can adapt under unstable wireless conditions. We review four major mobile edge computing architecture: single tier, hierarchical, collaborative, and fog-based. Each architectures offer trade-off in latency, scalability, and deployment complexity. The taxonomy also cover deployment models, resource provisioning, visualizations, orchestrations, and security. Despite these advances, handling heterogeneity across diverse mobile edge computing setup remains a challenge, especially when device and networks vary widely in capabilities. Task uploading is central to mobile edge computing literature. Mobile edge computing. The literature identifies local, partial, full, and cooperative uploading models. Each balances latency and energy differently. We also see the mathematical foundations, which highlight trade-off between local execution, transmission delay, and edge execution. While this model improves efficiency, energy sustainability in large-scale deployment, it is still unresolved, particularly for battery-constrained IoT devices. Deep learning models such as CNN, RNN, auto-encoders, transformer, and GANs are increasingly applied in mobile edge computing. They enable intelligent sensing, anomaly detections, and adaptive control. However, their complexity makes deployment at the edge difficult due to and also large models consume significant memory and energy. This motivate research into lightweight architecture, then compressions and collaborative inference, and efficient edge deployment of complex deep learning model, which remains an open gap. So reinforcement learning approaches such as Q-learning, SARSA, actor-critic, and DRL are widely used for adaptive resource management in mobile edge computing. DRL in particular shows promise in dynamic environment by learning optimal offloading and scheduling strategies. Yet scalability and real-time adaptability remain a challenge. Current reinforcement learning methods often struggle when scaled to millions of devices or when network conditions fluctuate rapidly. Recent literature highlights federated learning and transformer-based models such as TinyBird, mobile VIT, and Edge Former. These solutions address privacy and scalability concerned by enabling collaborative intelligence without sharing raw data. They also optimize inference for edge devices. It still privacy preserving analytics at the edge is not fully resolved, and federal learning remains vulnerable to attacks, and transformer deployment requires further optimization. So this table is the key theme for my prior work and highlights the gap and motivate my research. First is MSc mobile edge computing evolutions. We see a clear shift from central existing studies struggle with latency-aware learning under unstable network condition. Second is architecture. Different architecture have been explored. Single-tier, hierarchical, collaborative, and fog-based. The gap lies in handling heterogeneity across diverse mobile edge computing setup, which remain unresolved. Task offloading, strategies including local, partial, full, and cooperative offloading, each with latency energy trade-off, but scale deployment is still a major challenge. Deep remain an open problem. Uh, so taken together, this finding shows that while that simultaneously ensure stability, scalability, and efficiency. This gap directly motivate my proposed model, Deep Edge SARSA and Tara. So from the comparison table, the gap is clear. Existing strategy either SARSA. This model integrate eligibility trees with well-had design to stabilize learning and achieve balanced delay energy trade-off in cloud edge IoT and analytics. So building on this on literature review, one of the most critical gap identified is the lack of balance delay energy trade-off in the existing mobile edge computer system. Now methodology. To address the gap we identified earlier, we propose two reinforcement learning framework, Deep Edge SARSA and Tara. Now, Deep Edge SARSA is our first step. It extends the SARSA algorithm with a deep neural network and integrate eligibility trace. This improved temporal credit assignment, meaning the agent can link delay reward back to earlier decisions more effectively. The design also use a dual head architecture. One head estimate the action value function, while the other estimate the state value function. This operation stabilizes learning and reduce variance, which is crucial in dynamic mobile edge computing environment. Now, building on this Deep Edge SARSA, Tara trace-aware reinforcement architecture generalizes the approach. It supports multiple reinforcement learning paradigm, which includes SARSA, Q-learning, and actor-critic method. Head to enable multi-agent collaboration, making it scalable and heterogeneous. Mobile edge computing systems such as vehicular network and UAV-based deployment. Together, Deep Edge SARSA and Tara provide a progression from stabilizing single agent learning under delay reward to enabling scale cooperative and energy efficient offloading in a complex environment. So what is Deep SARSA? Deep SARSA is my first deep reinforcement learning contribution. It extends SARSA Lambda by integrating eligibility, improves temporal credit assignment under delay reward. This makes it suitable for volatile mobile edge computing environment. So this model is our first implementation of trace-aware reinforcement learning for mobile edge computing. The architecture has 4 channels, transmitting them to edge server, processing them, and reinforcement learning making uploading decisions. The novelty lie in 2 aspects. One is eligibility to trace. This allows the agent to link delay reward back to earlier action, improving temporal credit assignment. Dual head neural network. One head estimate action value, while the other estimates state value, stabilizing learning under noisy or delayed feedback. Together, these innovations reduce reward variance and improve responsiveness compared to conventional deep reinforcement learning method like TQN or PPO. System model of deep SARSA. Now here, each task is defined by 3 parameters. As data size in bits, this determines how much information need to be transmitted. C reduces required CPU cycle. This reflects computational intensity of the task. And D is a deadline constraint. This set the time sensitivity, which is critical for latency sensitive applications like AR or autonomous driving. Now, task arrival. Tasks don't arrive in steady stream. Instead, they follow a Poisson process, meaning arrivals at random and often bursty. This randomness creates periods of congestions and idle time, making resource allocation unpredictable. By defining tasks this way and modeling arrival as Poisson, we capture the uncertainty that reinforcement learning agents must handle. The channel gain edge varies over the time due to relay and Rayleigh fading, which reflect real-world fluctuations in single strand. The transmission rate is derived by the Shannon's capacity formula. Here, in this formula, here B is the bandwidth, PI is transmit power, and O is noise power. Is a noise power. Once tasks arrive at the edge server, they enter a shared queue with a limited service capacity. The queue state QT evolves based on the arrival AT and service rate ST. This formula captures congestions and a delay, especially during bursty task arrival. Next is in mobile edge computing, every decision's local execution or uploading comes with a trade-off in delay and energy. So here is the formula that we have used for the local delay. Offloading delay, which include transmission plus queuing latency and energy model. To enable intelligent offloading decisions, we model the mobile edge environment as a Markov decisions process. Here again, the state space S include buffer capacity, buffer occupancy, channel gain, task attributes, CPU frequency, and queue state. Action space A is either 0 or 1, 0 for local execution and 1 is for uploading, and reward function is provided. This is the reward function. So here the goal is to learn an optimal policy by that maximize expected accumulative reward. So this MDP formulations set the stage for our reinforcement learning agent, Tara, to learn delay energy optimized uploading strategy in real time. This is the algorithm for deep edge SARSA. This algorithm describes how deep edge SARSA operate in our cloud edge IoT environment. It extends the classical SARSA reinforcement learning method by each time steps the chosen action is executed. Task may be processed locally, uploaded to the edge, or sent to the cloud. We then compute the corresponding delay and energy cost. The temporal difference error is calculated, which measures the gap between the predicted and actual outcome. Eligibility traces are updated